Thank you very much for the introduction. At first, this work has been carried out in a cooperation with the Chemnitz University of Technology, with its chairs of Center for Microtechnology and Lightweight Structure Engineering and Polymer Technology, and the Fraunhofer Institute for Electronic Nanosystems and Applied Polymer Research. And my name is Robert Schulze, and I will present you in the next few minutes something about this topic. And here's my outline. At first, I want to start with an introduction. Then I will tell you a little bit more about embedding piezoelectric sensors, and furthermore about the characterization of these sensors. And I will finish with a conclusion and an outlook. At first, what is our motivation to do this work? This is so-called smart systems integration. So our main goal is to build up or develop smart systems containing of power source, energy management, and also with a communication unit, which is necessary to correspond with the environment, if we need antennas and so on. And furthermore, to make the system smart, we need sensors and actuators, which could be read out with smart electronics, with ASICs and so on. And therefore, the main point is we need integration technologies, and also integration technologies to integrate these smart systems in lightweight structures. Therefore, we have two strategies and two main projects at the moment. The first one is the integration of MEMS and also electronics in lightweight structures within the MERGE project. And the other one is to directly integrate the piezoelectric sensors into lightweight compound structures, as you can see on the right side. And this is something I will tell you more about in detail. First, we need piezoelectric sensors. Therefore, I prepared only one slide. We use PVDF, TRFE, and PVDF in different thicknesses, and they could be manufactured with different technologies. And on this picture, you can see such a PVDF copolymer transducer in the size of a sheet of paper. Then afterwards, you need to metallize it with, for example, some different electrode materials or novel materials, polymers such as P.PSS and semiconductors for other applications like ITO, or what is very interesting are CNT composite materials as electrodes. And afterwards, we have to do electrical polling to have a good polarization, that you have the piezoelectric functionality. And with this, such a piezoelectric sensor is ready for the embedding, for the integration into fiber-reinforced structures. And therefore, we have main aims. The first one is the optimal positioning of the piezoelectric sensors within the component to get a very good sensitivity and to measure accurate signals. The other one is the use of a technology without additional layers, such as adhesives. One interesting point is that you can encapsulate everything and to protect the sensors for harsh environments. And one interesting thing is it is possible to manufacture plain on the left side, and on the right side also curved structures. The right one is manufactured by hand laminate and contains, for example, 4 piezoelectric transducers, and the left one only 1 piezoelectric transducer with a CNT composite electrode. And I will tell you more about the characterization of the plain structure. Therefore, some words to the manufacturing, the real integration and embedding process. You have to place these piezoelectric sensor with connections into such a mold, and then you fix also these glass fiber reinforcements, and then you put everything together and inject the resin. This is called resin transfer molding. After this process time of approximately 18 hours, you can deform such a component, and this component is ready for characterization or to be used as a sensor in a further structure. At first, we started with a characterization with non-destructive tests, and to see how good is the sensitivity. Therefore, we built up a drop test, such an impact test, and we drop a steel ball of a weight of 12 grams onto the surface. And the interesting point is that the sensor behavior is approximately linear for different drop heights, and but which is much more interesting to see that we have we dropped the ball onto different positions, and the dependency of the location is not that much that expected. So we can drop, for example, on position 1 and position 7, and see also very good signals, because the main phenomena is the propagation of the acoustic waves within the component, and you measure this signal, and to and this could be used, for example, for an embedded acoustic emission sensor. Yeah, and we clamped this sample on both sides, and which is interesting to see in the FFT is that we excite all the fundamental frequencies in the longitudinal and the transversal direction, and so you can monitor the behavior of the component itself and not only of the piezoelectric sensor. Furthermore, we try to stress the component a little bit more. Therefore, we did 3-point bending tests, and to see where is the maximum load and where is nonlinear behavior. On this, you can see we measured up to 75 Newton with a linear behavior, and with a compliance of 0.11 meter per Newton, and the sensor, the whole component survives a maximum of 150 Newton without visible damage. So on this picture you can see this deformation on the maximum with 150 Newton is approximately 22 millimeter. So that's a lot. Furthermore, we tried to measure in parallel the electrical signal, and for different displacements and also for different bending speeds, and we tried to measure the dependency of the charge generation in dependency of the time, and also for different displacements. And what is interesting, we expected the linear behavior, but it's not measurable with this machine, because this is the region you want to measure. This is the interesting point you want to see, but which is much more interesting, you have more influences from the bending machine itself. So you have the approach and the release of the sample, and this does much more signals than the measured signal you want to see. In consequence, we can say that such a component is also useful to monitoring highly dynamic processes. Furthermore, we did impedance measurements on different samples to study the quality of embedding before and after the 3-point bending test. And on this slide, you can see the impedance curve for before and after embedding. And something which is very interesting, the red curve is the one after embedding, that you have a slight shift to lower frequencies and a small damping. So, and the consequence of it, we will see, or we want to see how does it influence the clamping of the sensor itself. Therefore, we made further measurements with different samples. The first one is a free sample, only the piezoelectric sensor itself, then the sensor after embedding, and furthermore the clamped sensor with a clamping force of 190 Newton per square meter. So, and what is interesting on this point, if you use the embedding process, the sensor is clamped more, and so the this plateau is shifted to higher frequencies, to the strong clamping. Yeah, and one further result is very interesting. We see that the thickness mode of the piezoelectric transducer itself is also damped while embedding, and yeah, everything is a result of the different mechanical properties of the component itself. Yeah, finally, we built up a demonstrator to show the feasibility of the integration of the piezoelectric sensor sheets, and the demonstrator setup consists of the sensor itself, the embedded sensor, and furthermore a signal conditioning circuit. And we modeled everything and did simulations to model the mechanical excitation. We can apply different forces, for example, or vibrations, or different mechanical signals. And then we modeled we did lumped element modeling to describe the transduction behavior of the piezoelectric sensor, the mechanical properties of the sensor, the transducer behavior itself, and also the electrical properties of the sensor. And furthermore, we made the signal conditioning of their for the demonstrator setup, because we wanted to show that it is possible to switch on and off light emitting diode with these piezoelectric sensors, and to have a good illumination, you have to define the threshold very well, and yeah, therefore we calculate the values of the corresponding resistors to switch on these light emitting diodes, and we can use it in a complete simulation, lumped element simulation with a network simulation tool, and finally this looks like this. You have this demonstrator with a piezoelectric sensor. In this case, we had different versions with metal electrodes and with CNT composite electrodes, and you can bend it, and then you can see the signals over this value that the light emitting diode is switched on. Yeah, finally, let's come to a conclusion. And I showed you that it is possible to embed piezoelectric sensors into fiber-reinforced composite structures, and this might lead to new or improved applications. And therefore, the smart systems integration approach is very helpful for design and characterization of these structures. The manufacturing of plane and curved structures was possible, and yeah, the electrical impedance could be used as a criterion to evaluate the quality of the piezoelectric sensors. And furthermore, these structures can be used for structural health monitoring, such as impact detection or acoustic emission. And the outlook will be to have a detailed characterization of the curved structures as well as destructive tests. And yeah, I think the most important point to conclude is we can combine this also with the embedding of smart electronics in such lightweight structures to enable new and tailored systems in whole components as a complex thing. Yeah, acknowledgement. Thank you very much for your attention, and yeah, that's it. Yeah.